Hello everybody, welcome back. Today we're going to have a little bit of a brief interlude, talk about hypersonic flow, which is kind of our last little miniature topic before we embark on the propulsion front. So today after the hypersonic section, we're going to kind of do an introduction to propulsion, some key definitions, go back and review some key thermodynamic cycles that are important, that allow us to define some efficiencies that will be important figures of merit and values that you'll be chasing in your homework, for example. So let's go ahead and get started. What do we mean by hypersonic flow, for example? So hypersonic flow, the thing that I want you to have in mind is think of very extreme conditions. Think of like a capsule or the space shuttle re-entering. So very extreme, such as the capsule / shuttle reentry, or a more current example would be like Starship, right? The capsule, just to put a number on it, re-entered at Mach 36, and the shuttle re-entered at Mach 25. I don't actually know what Starship re-enters at these days. But we also have like hypersonic weapon systems and a couple of concepts for hypersonic flight systems that have been developed. Typically, the line for hypersonic flow is drawn at Mach equal 5. So you would consider any flow or object where it's traveling greater than Mach 5, that's what we consider hypersonic. Okay, and so here are some images of, so the top right is a simulated aircraft, just a concept. I don't think it was ever actually constructed. On the top left, you can see a hypersonic missile or weapon system, and then those sort of re-entry processes that I alluded to before, like capsule on the bottom right, and Starship on the left, where you can actually see that when you start to encounter these extreme high speed flows, the heat involved becomes very extreme, and you generate a plasma even, which we'll talk about in more detail, but that has its own issues associated with it. So definitely a very extreme regime, and that's what I want to keep you in mind. But let's talk a little bit more about the actual details involved here. So one thing that's typical of hypersonic flow is that the shock, we end up with these things that we call shock layers that are very thin, and I'll describe what I mean by that. So in hypersonic flow, the space between oblique shocks and the physical boundaries become very thin. Space between oblique shocks and physical boundaries becomes very thin. Okay, and so as an example, consider a 15-degree wedge in m equals 36 flow. So from oblique shock theory, we would get that theta is equal to 18 in this case. And so what it would look like is the following, where you have this very thin wedge, right? And then the shock is, only 3 degrees separated from the surface. So this larger angle here is 18 degrees, and then this smaller angle here is 15 degrees. And in fact, this is even a little exaggerated. The layer would be even closer to the surface. But this sort of space here is what we term the shock layer. Okay. Let's go ahead and make sure we're using our normal highlighting convention here. So that's what the actual situation looks like. Let's make this a little more clear here with the diagram. Okay, and then there's this concept of the entropy layer. So for blunt objects, the detachment distance is also very small. So for blunt objects, the detachment, now remember the detachment is, for a blunt object in a supersonic flow, you end up with that sort of region. You have a normal shock directly upstream of the object, and that region between the normal shock and the object itself, you could consider to be a shock layer, and that region becomes very, very small for large n. So detachment distance, and that's the size of that region I'm describing, is also very small for a large Mach number. And then there's this point that neighboring streamlines through the normal part of the shock experience much different changes in entropy because it's so extreme. So neighboring streamlines through the normal part of the shock experience much different entropy increases. Delta S, and this leads to strong entropy gradients. Which in effect screws up your boundary layer calculations. And now we're getting into sort of viscous fluid mechanics, which is a course that you may not have taken by this point. But first, let me sort of just draw what I'm describing here. So imagine you have this blunt object here, and then you have a normal shock that's formed upstream of it, like that, and then the entropy layer is sort of this region here that I'll sort of, let's do this a different way. Let's do this like with a highlighter that's gray, like that. So this region here that I'm sort of shading in light gray, that is our entropy layer, and that's where you have those really strong entropy gradients that screw up your boundary layer calculations. And so what do I mean by screw up these calculations, right? So let's talk about this. And like I said, you may not have studied the boundary layer in detail, but I'll make sure to sort of give you the big takeaway here that you need to remember for when you're operating in the hypersonic regime. So because we have these extreme high rates of dissipation because of these strong entropy generation happening, so very high rates of dissipation. You end up with very high temperatures, and that's sort of exemplified by, the re-entry scenario where the temperature is so high that you're actually producing a plasma. So if we were to plot the temperature as a function of distance away from the surface, so let's say you have y here, and then this is the x-axis is going to be both the distance along the surface, so location, but I'll also be plotting the temperature on this, the temperature profile. What you have here, this is the boundary layer edge, say, kind of up a certain distance away from the surface. So that's the boundary layer edge. And then we also have our, flow over out here has a, we'll call it Mach infinity is huge. It's much, much greater than 1. And we'll say that we have some sort of temperature of the free stream as well, T infinity. And we'll follow that up. And so the temperature rapidly rises as you enter the boundary layer to very, very high values. And then sort of, drops down to whatever value the wall is experiencing as a result of this. And so what happens is you have high temperature in the boundary layer, which leads to low density and high mu, okay, your viscous coefficient, which gives you a thicker boundary layer. Thicker boundary layer, and the resultant scaling sort of looks like this. This delta BL is the thickness of the boundary layer, and it's proportional to the free stream Mach number squared divided by the square root of the Reynolds number in along the surface in that direction. And so the takeaway here is that the increased size of the boundary layer makes the effective size of the body much longer, or larger, I should say. Body much larger. And by size here, I mean like cross-section. So remember that all of our sort of airfoil calculations they essentially start where the boundary layer ends. And usually the boundary layer is thin enough to where you can essentially just use the same shape of your airfoil and assume that you have ideal flow almost instantly as you at the surface of the airfoil, at least for simple analyses. But in this case, the boundary layer starts to get thick enough where the cross section of your airfoils and your overall device becomes significantly larger, and it becomes a problem and messes with things. Okay. What else can we say about high temperatures? Well, let's look at the capsule scenario, right? So imagine you have a capsule that's re-entering. I'll label that since it's not very clean. And then you have this sort of normal shock that's forming in front of the capsule. It's actually very closely detached. And if we zoom in on this region close to the capsule wall, you have the normal shock, whoops. And then you have the capsule wall here. And in the capsule case, I mean, you're talking a temperature of 11,000 Kelvin. Okay, and that is going to produce a plasma. And plasma, has a bunch of downsides, especially when you're trying to communicate. So like high temps not only can lead to plasma, but they can also lead to chemically reacting flows. Which brings into a whole host of more complications, or even ionization, and that's the plasma case. And for the reentry of space vehicles, that's where you get the communications blackout, because our communications bands do not penetrates the plasma of the density that forms on the Earth-facing side of these vehicles. So that's one particular issue that you can end up with these really, really extreme hypersonic flows. Let's do a little bit of mathematical reasoning or quantitative reasoning in the hypersonic limit. So we'll call this section hypersonic oblique shock relations. Okay, and we'll start by drawing our typical oblique shock diagram here that we've drawn over and over again. We have our oblique shock occurring here at a shock angle theta, and then we have our parallel component and our perpendicular component. On the other side, we get this slightly deflected M2 with the same parallel component as before, and a smaller perpendicular component there. And that overall deflection angle we'll call delta. Okay, so what we're going to do is examine all the oblique shock relations in the hypersonic limit. Shock relations in the hypersonic limit. Okay, so let's look at pressure, for example. So for pressure, P2 over P1 in the oblique shock case is equal to 1 plus 2 gamma over gamma plus 1 times this quantity m1 squared sine squared theta minus 1. And if in the case where your Mach number, m1, your upstream Mach number is super large, all these other constant terms are going to be negligibly small compared to the term that has the m1 squared in it, right? So this in the limit just becomes 2 gamma over gamma plus 1 times m1 squared sine squared theta, okay? Because those constant terms are going to look de minimis compared to the term that has the Mach number, which is very large. We're sending, by the way, the hypersonic limit is basically sending m1 to infinity, right? Saying it's getting very, very large. I really shouldn't say that. I should say saying that m1 is much, much greater than 1. That's a more precise statement. What about the density? Well, the density of rho 1 over rho 2 is usually equal to gamma plus 1 times m1 squared sine squared theta divided by quantity gamma minus 1 times m1 squared sine squared theta plus 2. And that, in the large M limit, actually just simplifies to gamma plus 1 over gamma minus 1, right? Just sending m1 to infinity, essentially. The temperature case, we have T2 over T1. We can actually rewrite this as P2 over P1 divided by rho 2 over rho 1. just using the ideal gas law equation of state, and you end up with 2 gamma over gamma minus 1 divided by quantity gamma plus 1 times m1 squared sine squared theta. Okay? So here are these 3 things in the hypersonic limit. The other thing that's interesting is to take a look at the deflection angle. So normally we have this relationship here that the tangent of the deflection angle is equal to twice the cotangent of the shock angle times this quantity m1 squared sine squared theta minus 1 divided by m1 squared times gamma plus cosine of twice the shock angle plus 2. Well, we know that in the hypersonic limit, we're going to have a very, very small shock angle. And we also know that the deflection is also going to be very, very small. Right? So when we include those 2 simplifications, sine theta basically looks like theta, right? This is like from the Taylor series expansion. Tangent theta, or tangent delta, is also likewise just looks like delta. And then cosine of 2 theta, the very small 2 theta, just looks like 1. And so what you end up with is that delta is approximately equal to 2 over theta times the quantity m1 squared theta squared minus 1 divided by m1 squared gamma plus 1 plus 2. So that's what you get there, right? So now we'll go ahead and send m1 to be very large. m1 is much greater than 1. And then what you end up with is that the deflection angle is essentially a constant. That is just it's directly proportional to theta. So theta over delta, the ratio between the 2 is gamma plus 1 over 2, or 1.2 for air, our main case, right? And this is sort of hidden in our prior example, 15 to 18 degrees in the prior example. Okay, so the relationship between the shock angle and the deflection angle is very simple in the hypersonic limit. Okay, and so there's obviously more intricacy involved with hypersonics, but hopefully this sort of, first of all, this analysis where we're taking the limits here makes sense. And then, if you're inspired by these types of applications, and you think this is interesting, well, you know where to look, and now you have a little bit of a start. But now I would like to shift gears and give an introduction to the propulsion topic, which in my opinion is where things get interesting, in particular in this class. But first, we do have to go through a lot of definitions and review material. So we're going to do that in this lecture. So first off, let's talk about general types of propulsion systems. And I should say, before we get started, this whole propulsion topic will not be found in Zachariah Dublar's, which has been our primary written resource up to this point. This is actually adapted from Professor Cantwell. Professor Cantwell's propulsion course. At Stanford University. Okay, and it's all of his materials for that course are open and free. So if you want to go and find the textbook for the course, I encourage you. I think it's just a term to course reader. But I took this course, thought it was very nice. And so I've taken some of the more accessible parts of it that depend on the stuff that we've learned up to this point and repackaged it as the kind of last unit in this class. But that's so if you're looking for text to back up and expand more upon the things that we'll be talking about from here on out, go and check out Cantwell's course reader as opposed to looking in Zucker and Biplar's, which is the main resource for this class. Okay, so let's proceed. What are some types of propulsion systems? Well, one thing is a standard piston engine, which is like a traditional propeller engine. Some of the first engines ever produced. We're first learning how to fly as a species. And then we also have gas turbine engines. So this is where you take free stream air, which is, low pressure and also subsonic. So we're still operating in the subsonic regime here. And then you take that through the engine, taken through engine. Okay, some examples of these are like turbojets, turbofans, and turboprops. These are all types that you'll find in commercial airlines today. So, and in fact, they're propulsion systems that we'll go through in great detail in subsequent lectures. We also have air-breathing jet engines. Sorry, that's hard to read. Air-breathing jet engines. So this is where you have free stream low pressure supersonic flow. Taken into the engine. So examples of this are like the ramjet and the scramjet, which itself is a topic of active research. Okay. We also have rocket engines. So this is where you carry on board fuel and oxidizer. Which is in contrast to the other options because they're using the free stream as the oxidizer, right? And then this is just accelerated through a nozzle. We won't cover rockets in detail because there's a rocket propulsion class at Oregon State. It's taught by Dr. Niemeyer, so I encourage you all to take that course. It's another, I think it is a 400 level course in the department. So you can learn about rocket propulsion in that class. And then there's one more type of propulsion system which you would just call electric aircraft propulsion. And really, this is, you use electromagnets to turn propellers. To turn propellers, and this is like a drone. your typical hobbyist drones would use this propulsion, but not super useful for transporting humans and or weapon payloads. Let's get down to brass tacks and really start defining some of our important metrics here. So there are two important metrics in particular. Okay, one is thrust, which is the force generated along the engine axis. And then the other is specific impulse. Or what you can call thrust-specific fuel consumption. Thrust-specific fuel consumption, or TSFC. Okay. So what are these guys? Well, T is how we denote thrust. It's in the units of thrust are like newtons or pound force, essentially units of force, of course. And then specific impulse is ISP. Okay, that's the way it's denoted. And it's defined as the thrust divided by the mass flow rate of the fuel times G naught. Okay, which is the acceleration due to gravity at sea level. And then this is in units of seconds. And we're talking about the propellant here. So this is not just fuel, but for a rocket, it would be fuel plus oxidizer. So mass of propellant for rocket m dot f is equal to m dot fuel plus m dot oxidizer, just to be clear. And then TSFC is defined as 1 over G naught ISP, or it's just m dot f divided by the thrust, normalized by the thrust. Okay, that's the relationship between TSFC and ISP. And really, you're just looking at the thrust that you're getting out per the weight of the propellant that's being thrown out of your propulsion system. That's what the specific impulse is telling you. Okay, it's a metric of efficiency. So let's go through some quick basic aerodynamics here. So let's imagine that we have this airfoil here, sort of positive angle of attack, and we usually draw a chord from the tip of the airfoil through the center, and that chord defines our angle of attack. So this angle here is we'll call alpha, angle of attack. Okay, and then what you end up with is you have some effective lift, which is composed of the contribution of pressure, the pressure distribution, in the sort of component in the direction that's normal to the airfoil cord, and also there's this lift-induced drag here. Okay, so that's the drag that doesn't have to do with the friction on the airfoil. That's the drag that has to do with the geometry of the airfoil itself. And I should also note here that we have some sort of free stream that's traveling sort of directly to the right here. That's that. So the angle of attack is defined relative to the free stream flow. We usually define these coefficients of drag and lift, where CD is equal to D over 1/2 rho infinity V infinity squared S. This is the free stream velocity and density, and then S is the surface area. And then we also end up with a coefficient of lift, which is our lift force normalized by the same thing, rho infinity squared rho infinity V infinity squared S. This sort of quantity here is termed the dynamic pressure Q infinity. Okay, and then our total drag, or we have this concept of total drag, I should say, where our total drag coefficient is actually made up of CdP, which is your parasitic drag. Parasitic drag, and that is the viscous drag. That's the, has to do with the boundary layer. That's like friction, right? And then there's the lift-induced drag, which is CDI. And that's what we just talked about a moment ago. Lift-induced drag. Okay? And CDI we can express as CL squared over pi AR. AR is one quantity times E. AR is the aspect ratio. And E is the span efficiency factor. Okay? So just a bunch of definitions. So let's go through an exercise here, and we're going to maximize the ratio of the lift to drag. Okay, which is the same thing as CL over CD. So let's maximize L over D, which is the same as CL over CD. And we'll see from this exercise, we'll see some interesting things. So first off, if we take the partial derivative with respect to CL of this ratio, CD over CL, then what you get is you end up with negative CdP divided by CL squared plus 1 over pi AR E. So we split up the coefficient of drag into two components, and then we differentiate it with respect to CL. And we set that equal to 0. And if we solve for CL, like an optimal coefficient of lift, to maximize this ratio, what you end up with the CL star, we'll denote it that way, is equal to the square root of pi times the aspect ratio times E times the CdP, which you can then calculate CL over CD max as 1/2 square root of pi AR E over CdP. Okay? So that's one answer for how for what you could optimize for. So your by the way, your coefficient of lift is sort of that is what you change from your design parameters. That's why we're optimizing for that value, right? So like, how much lift do you how large can you make your lift if you're trying to optimize for the ratio between your lift and drag, right? That's essentially the question that we ask first. But another thing that you can try to maximize is your range. So if I were to draw like an aircraft here, you can denote the forces in each direction by the quantities that we've just derived. So the force acting upwards is L. The force acting backwards is the drag. The force acting forward is the thrust, and then the force acting downward is the weight of the aircraft, right? And if we want to, minimize our fuel consumption and maximize our range, we want our ratio of distance over fuel, which we can write as U infinity times some time that we've been traveling divided by our thrust specific fuel consumption times, normally we would multiply that by the thrust to get the mass fuel rate, right? But we're going to multiply it by d because we know that d is equal to t. So we're at steady state. Assume steady state. So we're cruising, right? So thrust specific fuel consumption times d would be equal to m dot f times our time. That's going to give our total distance used divided by our total fuel used. That's what this whole quantity is here. The thrust falls out, and you can rewrite this again by essentially multiplying by 1, which would be multiplying by L over W, since L is equal to W in steady state. So you have U infinity, we can pull that D into the denominator as L over D. And then the bottom, we still have TSFC down there times this time the weight, okay? And then we pull out TSFC, 1 over TSFC. And then we pull out some other constants here. We get 2 over rho infinity S times the weight. This is just plugging in the definitions or introducing the lift and drag coefficients, and you get CL over CD total. And then if we maximize this with respect to CL, then we get a different CL, right? So our CL CL star in this case is the square root of pi AR E CDP divided by 3. Okay, I'll just note this is the range CL star. So comparing these two here, they're actually very, very similar. One of them is they just differ by a factor of the square root of 3. But it is different, right? So if we were to plot, and we can see this on the plot, so if I plot the rho infinity V infinity squared S CD, right, this is what the drag is. If I plot the drag as a function of our free stream flow velocity, which is our cruising speed, V infinity drag, then you end up with something that looks like this, right? And our maximum possible thrust looks like that. And so this sort of forms the frontier of our minimum flight speed. And then our maximum flight speed on this side. So this thing is our max thrust. Okay, so within that frontier, we can choose our design, making certain trade-offs, like how do we want the ratio of lift to drag to be? Do we want to optimize for that, or do we want to optimize for our maximum amount of range? And interestingly, we don't get the same answer in both cases, say, depending on what we're optimizing for. But this maximum thrust plot here shows you what our range of flight speeds is limited to being, given the way our drag shakes out. Okay, our drag coefficient values. All right, so that's kind of a little roughshod, a little bit of a shotgun blast there, but just it's just an exercise in getting familiar with the old terms and measures of efficiency. But now let's go and do some review of thermodynamic cycles. Okay, so the most efficient thermodynamic cycle between two thermal reservoirs is the Carnot cycle. Most efficient between two reservoirs. So what do we mean by that? Well, we're going to draw the different steps of this cycle. So imagine we have a piston system here. It starts off at T1, and then it undergoes an adiabatic compression down to a temperature 2. So this is adiabatic compression. Okay, and then it goes into contact with the thermal bath, let's say, and it has an isothermal expansion. Okay, and that's where you have that heat that it's taking from that thermal bath. Then you have adiabatic expansion, where the piston will move up even more and return to temperature 1. Okay? And then it goes into contact with the, let's say, cold bath, and returns to its original state with T1, and you have some sort of Q out, right? This is an isothermal compression. Okay. So if you draw the TS and PV diagrams for the Carnot cycle, those are very, very, canonical. I'm sure you've seen them before. The TS diagram just looks like a square for the ideal Carnot cycle. You start here, you go straight up through that adiabatic compression, and you go straight over through the isothermal expansion, Go straight down through the adiabatic expansion and then back over to the isothermal compression. So this is like state 0, 1, 2, and 3. Okay, and the heat addition is happening here. So this is like Q in, and then you have the heat exiting the system, Q out here. Okay? The PV diagram, you see the sort of isentropes and isotherm processes. So you start, 0 here, and you're going up adiabatically or isentropically. So it's a little bit steeper, and then you get a 1 over V for the isothermal branch, and then it's like this down to state 3, and then you get that isothermal to complete there. Okay, so this is where you have that dt equals 0. This is ds equals 0. Okay, and they go off in this direction, and we'll label the states on here as well: 0, 1, 2, and 3. And then just remember that, the areas of these things tell you the heat, delta Q, say, and then the area of this guy tells you your work, because it's PDV. The integral of PDV is the area of that diagram. So what about efficiency? What we'll call thermodynamic efficiency. So our work out that we get net is going to be equal to Q in minus Q out, right? That's just from the first law. So we can define an efficiency, eta, which is work out for how much heat you put in. And we can rewrite that as 1 minus Q out divided by Q in. Okay? And then for the ideal Carnot cycle, we know that the integral over all steps of the entropy is equal to 0, the closed, because it's ideal. So that tells us that Q in over T in minus Q out over T out, just by doing that integral, is equal to 0. And so the ratio of Q out over Q in is equal to T out over T in. And then what you end up with for the so-called Carnot efficiency is 1 minus T out over T in, or in other words, 1 minus TC over TH, the ratio of the cold bath to the hot bath. And remember how I said Carnot intuited this efficiency by thinking about caloric, but this is the proper way of doing it, actually integrating over the thermodynamic processes. Okay, so that's your most efficient canonical thermodynamic process. Another very important one for propulsion is the Brayton cycle. So let me So the Brayton cycle, I'm going to draw the same sort of five pistons here. And we'll just start with actually drawing the pistons as they are, and then we'll talk about what's happening in between each step here. I'll give myself quite enough room here. Okay, and so we'll start with this position, let's say, P1 at pressure 1. And then you have an adiabatic compression. And I should say that anytime I'm writing down adiabatic, you know that if it's actually ideal, that means it's isentropic, right? But I'll go ahead and proceed. So we have this adiabatic compression down to a higher pressure P2 in the piston, and then we have an isobaric expansion. Isobaric expansion. So holding P2 constant, heat is added to the system, and so the piston expands upwards. Okay, and then you have another adiabatic expansion. So no heat transfer happening during this expansion up to the highest point, P1. Okay, so there's no heat transfer, but the pressure is changing. And then you have an isobaric compression. And this is where heat exits the system. And you return to your initial state with the pressure being equal to P1. Okay, so that's what the Brayton cycle looks like. Let's look at the diagrams. So the PV diagram is almost more straightforward than before. You started at that state 0, and then you have the adiabatic compression up, and you have an isobar, and you have another adiabatic compression, or expansion rather, to lower pressure. And it looks like this. So this is 0, 1, 2, 3, and the heat transfer is happening across these isobars. Q in, Q out. Okay? And then the TS diagram looks like this. 0 to 1 is, for the ideal system, is isentropic. And then you have, this is what the isobaric expansion looks like. And then you have finishing up the system like that. Okay? And if you had like inefficiencies, this would be like, happen like here. Something like that. Just to give you an idea, it's kind of a point off the cuff there. Okay, so that's what the cycle diagrams look like for the Brayton cycle. Let's talk about the efficiency. So we still have, of course, that the work is equal to Q in minus Q out. The first law says that our heat change is equal to du plus P dV, which can be rewritten as dH minus V dP, right? The heat transfer is happens where the pressure change is equal to 0. So any heat change is directly equal to the change in enthalpy for a Brayton cycle. And Q in is thus equal to H2 minus H1 rather. And Q out is equal to H3 minus H naught. Okay? And so we can write the Brayton cycle efficiency in the following way, where we have 1 minus H3 minus H naught over H2 minus H1. Okay, and then if gamma is constant, then H naught over h1, for example, is equal to t naught over t1, which is equal to p naught over p1 raised to the gamma minus 1 over gamma. And then that thing is also equal to p3 over p2, because it's the isobaric process, over gamma, and then those continue forward until you can say that this is equal to h3 over h2. So h naught over h1 is equal to h3 over h2, and we can sort of sub these in and rewrite the Brayton efficiency in a simpler way, where you get a to b is equal to 1 minus h naught times this quantity h3 over h naught minus 1 over h1 times this quantity h2 over h1 minus 1. And then we can write this in terms of the temperatures only. 1 minus T naught over T1 times this quantity T3 over T naught minus 1 over T2 over T1 minus 1. But we just showed that we just showed this relationship where if we cross multiply, we can say that T naught over T3 is equal to T2 over T1 over T2. Apologies for all the hand waving here, but this thing all goes to 1. Okay, and so the Brayton efficiency can just be written as 1 minus T naught over T1. So just the temperatures at the first two stations. Okay, so that's the simplified version of the Brayton efficiency. And we will proceed next time to talk about some engines that use this cycle as the basic thermodynamic cycle of interest. Okay, apologies for rushing through that. The room is hot, and I want it to be done. So hopefully I wasn't too rushed. The good news is that most of this should have been review, and if you missed anything, you should be able to go back and take a look at your thermodynamics notes and hopefully remind yourself what's going on with these cycles here. So yeah, next time we're going to go ahead and hop in with propulsion. Hope you enjoy it, but in the meantime, have a good one, and I'll see you next time.